Good afternoon, everyone. Welcome to the third presentation by our NASA subject matter experts on various projects around the agency. I'd like to say hello to everybody that's participating in the online course. We appreciate you guys attending this afternoon. Hopefully you've had a chance to take a look at Dr. Ashwin Vasavada's biography on the website and get a little bit more information about him. He's here today to talk about the NASA Curiosity rover. Dr. Vasavada is a planetary scientist at the Jet Propulsion Laboratory, which is in Pasadena, California. He's currently the deputy project scientist for NASA's Curiosity rover. So he's going to tell you a little bit about that project as well as some of the work that's gone into that. He's a veteran of quite a few different NASA projects, including the Galileo mission to Jupiter, as well as the Cassini mission to Saturn. So he's going to have a lot of insight into some of the things that you guys will be working on when it comes to your final project. So without further ado, I'm going to go ahead and turn it over to him. At the end of the presentation, we will do a question and answer session like we've done previously. So please hold your questions till the end of the session. And what we'll do is after the presentation, we'll tell you how we'll enter those questions and we'll go from there. So without further ado, I'm going to turn it over to Dr. Vasavada.
Okay, thanks a lot. It's great to be here to talk to you about the Curiosity mission. I'm going to go to the slideshow and turn off my video for the rest of the talk until I take questions. But I'll try to save plenty of room for questions, and I hope you enjoy what I have for you in the next 40-45 minutes or so. Okay, so I think everybody hopefully can see this first slide. This is one of our close-up views of the mountain near where we landed. I'll talk more about that in a second. But this just shows you some gorgeous views of the mountain that we're up against, and we'll be climbing for the next couple of years with this rover. And I'm Ashwin Vasavada, the MSL Science Team, Project Scientist currently, and representing the work of about 500 scientists around the world and a few hundred engineers who currently operate the rover here at JPL. And let's see, should I advance the slides, Jamie? How does that work? Yeah, okay.
Yeah, if you feel comfortable doing that, go ahead and do that. If not, I'll help you out.
Okay, no, I got it. Just found the button. Okay, so Curiosity. Hopefully you all remember when we landed a couple years ago. But this project's been in development now for, well, it had been in development since 2004, and even some scientific studies before that. So it's been around a while. I've been working on it now for 11 years, which is crazy. I'm amazed that I survived this long on it. But it was designed to be kind of a bridge between missions that looked at Mars geology in the past, looking at how much water may have been on the surface and how long that water persisted, and then future missions where we'll actually look for evidence of life. So what's in the middle? In the middle, between those two things, is what we call habitability. So Curiosity is built to be a geologist on Mars that studies whether Mars ever was habitable. So what it says on this slide here is our primary scientific goal is to explore and quantitatively assess a local region on Mars' surface as a potential habitat for life. And so what do we mean by a habitat? Well, we want to understand whether something could have lived there. That's sort of what a habitat means. And so we want to understand whether there were the right ingredients for life, the kind of carbon-containing molecules that are in all of our cells, and all the other chemical elements that life uses. We want to understand the geology and geochemistry, because those are the ways that we would understand the other things I just mentioned in the ancient past. So all the clues that we're looking for about whether Mars ever was habitable are now trapped in the rock record. So we have to be geologists and geochemists and see what we can, by looking at these ancient rocks, can we extract information about what the environment was like 3 billion years ago, and whether those ingredients for life were present. We also look at the modern water, weather, and climate of Mars and the current radiation levels on Mars, because we want to understand whether the present environment and hazards to life like radiation can help us learn something about the ancient past. Part of the reason we carry a radiation detector with Curiosity as well is to prepare for human exploration. So even though we're mostly a scientific mission, studying Mars habitability. We're also looking forward to having humans on Mars, and we carry a sensor that's the first to measure what the radiation environment that astronauts will have to put up with when they're on the surface of Mars. So this rover is pretty complex. It's a beast. It's more like the kind of spacecraft that we sent out to the outer planets, Jupiter and Saturn in the past, with a whole Christmas tree of instruments and a very complex computer and set of software that runs all of them. It's much more complex, for example, than the past rovers on Mars. But so here we're sending something that's the complexity of like one of those big flagship orbiter missions, and we're sending it to Mars surface with these 10 different instruments, all on top of this very capable fixed-wheel vehicle. It's about the size of a small car. It can drive over obstacles about the size of what's shown on this picture with the rock. So it can drive over something about the size of one of its wheels. And then it has this mast that sticks up about 7 feet off the ground. On the mast, there's some cameras that we do all of our color imaging with. And then that white box on the very top is a laser that's shown here in the picture called ChemCam. With that laser, we can shoot up to 20 feet around us and create little sparks. And by looking at the color of those sparks in great detail, we can figure out what the rocks and soils are made out of. So we can do even chemistry from 20 feet away. We also have this robotic arm, which is about 7 feet long. On the end of the arm, there's a drill, and that's one of the reasons the arm is so beefy. But there's also other instruments on the arm, like a chemical spectrometer that we place up against rocks, and then another imager, which is to do close-up pictures of rocks and soils. The reason we have the drill is because we are the Mars Science Laboratory, and the front end of the rover consists of 2 labs, chemistry labs. One called SAM, which looks at the chemistry of rocks and soils and the different isotopes of the different chemical elements that are in those, and one called ChemIn, which tells us what minerals are present in all the rocks and soils. And so the drill drills into rocks, gets the powder that it created while drilling, and then delivers that powder into these laboratories inside the rover. And then the remainder of the instruments are more environmental sensing, like weather and what's under the surface in terms of chemistry, and then a radiation detector. So it's a really complex rover, and part of my job as the project scientist is to channel all the desires of those 500 scientists around the world who want to do their experiments with this rover into a plan of what to do every day. And that's pretty tough because everybody has a lot of things on their wish list, and we have 10 different instruments, and yet we only have 1 rover and 1 battery to use to power everything. So we spend a lot of time every day. Actually, it takes about 10 hours every day to develop a plan to run the rover for the next day. So a little bit more background on the mission. We chose Gale Crater as our landing site because of all the places on Mars to look for places that once may have been habitable. This crater struck us as pretty interesting. Not only is it a crater that's about 150 kilometers across, about 100 miles across, but it has this big mountain in the middle of it. And this mountain is kind of unique. It's much bigger than you'd expect to have formed with the crater. So something else delivered the material that then formed this mountain. And then we also saw that it's layered. So it's not a volcano, which is kind of one big, massive, mountain, but it was laid down layer by layer in horizontal layers. And these layers change in composition with height, which suggests that the environment of Mars was changing as the mountain was being built up. And that's what's shown on this next slide, where here we've cut away inside the mountain, showing that it's made of horizontal layers. And then if you look in the lower right, you're kind of looking down on the ellipse that's drawn on the other image, and the mountain now on the lower right image. The mountain is in the lower right-hand side of that image, and you can see that the bottommost layers of the mountain are made out of clay, and then you go slightly higher up the mountain and you get layers made out of sulfate minerals, which both of which, clays and sulfates, both require water to form. So you take water, you let it interact with Mars rocks, and in some conditions they weather into clay. But then in other conditions, when there's maybe less water around and maybe the atmosphere was drying up over time, they weather into sulfates. And so the fact that the mountain has these layers that change with height, and which presumably means that they change with time, with the bottommost layers being the oldest, it means that this mountain may have a record. It may be like a book where every page as we climb up is a different time in Mars history. And that's what we really got excited about with this mountain. The last thing I'll talk about here is where we landed in this big circle that's drawn. That was the landing accuracy that we had. And what we already knew even before landing is that there was an ancient river system that spread out material in a fan across this area. And we expected to land pretty close to where this ancient river deposited its material. So we launched in November 2011, the day after Thanksgiving. We were all in Florida watching this big rocket take off, carrying Curiosity to Mars. And then August of 2012, we landed at 10:30 at night, in about midnight your time, really. Oh, actually, you're all over the country, so it was 10:30 West Coast time, and it was pretty fantastic. I think that was the most dramatic part of the mission so far, is landing here. Our heat shield had just come off. We're still a few miles above Mars surface, and the camera that was on during the descent was capturing those sand dunes, those dark sand dunes below. And our landing site's even down there somewhere about several miles below where this picture was taken. And then just before landing, we had some descent rockets that slowed the spacecraft down, and then a cable lowered the rover down to the surface. And I love this picture because it reminds me of the lunar landings back, a few decades ago, where, oops, that's my phone, where the dust is kicking up just as Curiosity is setting down on the surface. All right, so we then decided where we would go for our first scientific measurements. And this is a picture that was taken by the Mars Reconnaissance Orbiter, which is a spacecraft that NASA has had at Mars since 2006. And it takes these amazing kind of spy satellite quality pictures of Mars surface. And you can see at the site called Bradbury Landing is those rocket engines, like in the last picture where it's blowing all the dust off the surface. We left this big bluish mark on Mars, what looks like a bluish mark, where all the orange dust of Mars was washed away, and we landed right in the middle of that scoured area. And then we drove off to the right of this image because we wanted to get to this site called Yellowknife Bay. And you can see how dramatically the rocks change from the dusty covered gravel that's most of the left-hand part of the picture to the whitish, very rocky surface that's on the right-hand side of the picture. And that's actually the edge of that ancient river fan that I mentioned earlier. So we landed only 500 meters away from the edge of this ancient water deposit. And so we had to go check it out. And we actually spent a year there before we drove towards the mountain, which is our primary goal for the mission. So it was very opportunistic for us to land so close to the edge of that fan. And then you'll see that we made our biggest discovery of the mission so far, even before we ever got to the mountain itself. So we drove about this 500 meters. You can actually see the tracks of the rover on this picture from orbit. And you can even see the Curiosity rover perched right on the edge of Yellowknife Bay. It's just a couple pixels across in this image. So this picture is one of our earliest discoveries, although at the time we didn't really know that we had discovered anything yet. The rockets had scoured off the upper, couple centimeters of soil, and we saw this bedrock right where we landed. And this bedrock, from our Earth experience, it kind of looks like an old, worn down road that you might find deep in the forest somewhere where it used to be a paved road and then it's all washed away. And that's kind of like what it is. It's just natural, but it's a rock we call a conglomerate, which is a bunch of small pebbles that are cemented together by some other minerals. And then we had, it's now sort of eroding away, and part of our rocket engines scoured that off. And we didn't really want to make a big claim, the day after we landed, because we weren't sure what we were looking at yet. But it sure struck a lot of our geologists on the team as something that could have formed in flowing water. And in fact, the more we studied these same rocks as we saw them for another couple months, we realized that we were actually driving through an ancient stream bed on Mars, where all these little pebbles that are now in this conglomerate rock are rounded. They're like pebbles at the bottom of a river that you might see on Earth that have been transported and rolled along the edge of the stream, or the bottom of the stream, and all the corners were rounded off, and you end up getting this beautiful set of rounded pebbles. So this is kind of what it looks like, again, from a picture from orbit. Now here the colors represent the height of the surface. So we landed between the rim of the crater to the north, which is the high part where you see the Peace Vallis River coming down and spreading material in this fan. We landed in the low blue area where that ellipse is shown, and the little plus sign in the ellipse is actually where we landed. And then we have our target to go down towards the bottom of the screen to where the altitude starts increasing again, and that's actually the mountain itself in the middle of the crater. Okay, so after Yellowknife Bay, we then decided after we got to the edge of Yellowknife Bay, we then had to go into it and actually figure out what we were looking at, what all these whitish, light-colored rocky surfaces were. And so we carefully drove in there, and here you can see now we're actually inside Yellowknife Bay, and you can see how different the surface is. There's hardly any sand or gravel anymore. It's almost all bedrock, and it's all broken up into these little plates. It's very light-colored rock. And you can see this gorgeous picture with Mount Sharp, that mountain in the middle of the crater. Mount Sharp is in the background, and then our 7-foot robotic arm is extended, and it has currently the drill up against the surface, and we're getting our first sample of what these rocks are at the bottom of Yellowknife Bay. And, this is what we discovered. Our hypothesis going in was that we were following this stream bed to where we saw all this bedrock, and the bedrock turned out to be pretty soft and flat, and our interpretation, our hypothesis was that there may have been a lake bed here. So at the end of the river system would be where maybe there was a standing body of water, and the sediment from the river carried lots of sediment, and then that sediment slowly settled out into mud, kind of like the muck at the bottom of a lake that you might be familiar with on Earth. And when we drilled into the rock, that's what we found. We found all these different clues that suggested that Yellowknife Bay was actually a place that could have supported life in Mars' ancient past. 3 billion years ago, when the river was flowing and a lake was here, the conditions were all right for life. So what are those conditions? Well, we first have all the water. We have the evidence for the river system. We have evidence that what we drilled into was the mud at the bottom of the lake, and we know that from the very small particles that make up the rock and the fact that it contains a lot of clay. And clay is something that forms only when you have water interacting with rock. And so the mineralogy indicates also that the water was pretty fresh. It wasn't too acidic, otherwise the clay wouldn't have formed. It wasn't too alkaline. It wasn't too saline. It didn't have that much salt dissolved in it because there's not too many salty minerals that we found mixed in with it. And it wasn't too oxidizing based on other chemical information. Now, oxidizing would have been a bad thing for life. We also found trace amounts of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, which are kind of the big 6 chemical elements that life requires, and they were all present here for life to make use of. And then finally, we found a source of energy that organisms could have used. Of course, there was sunlight even 3 billion years ago that life could have used, but then we also found various minerals in various states of chemical oxidation. So we found sulfur that was both bonded to hydrogen and bonded to oxygen in different minerals. And so microbes on Earth can make use of those differences. They can look for sulfur or other minerals that have different states of chemical oxidation, and then make use of that to generate energy for themselves. And so when you have bugs deep underground, bugs meaning microorganisms, where they're away from sunlight and away from plants and other things, they can actually live off of those kind of chemical variations around them. So it was pretty cool. That's what we went to Mars to do. We wanted to show that it was a habitable environment, and Yellowknife Bay was habitable. We did not discover life. We did not discover any evidence for life. I wish we did, let me tell you. But so far, all we're able to say is that all the conditions were right for life. Okay, so then we headed out. You can see up on the top of this map, our landing site is a green dot, Yellowknife Bay in the blue dot, just 500 meters to the right. And then we spent about 15 months driving all the way from Yellowknife Bay to the site that's labeled base of Mount Sharp. So we spent about 15 months driving about 10 miles, or actually 10 kilometers. We've stopped at a site called the Kimberley to check out those rocks for about 2 months, then continued on, and we just arrived at the base of Mount Sharp, where the elevation starts going up dramatically as you climb the mountain, in September of last year. And so we've been studying the site called Pahrump Hills since about late September, and drilling into the first rocks that are actually part of Mount Sharp. And I want to tell you a little bit about what we discovered along the way. On that 15-month drive from Yellowknife Bay all the way to Mount Sharp, we discovered a lot more about what may have formed Mount Sharp. I mentioned earlier that Mount Sharp is made up of layered rock, and that some of the layers are clay, meaning the water was involved. Some of the layers are made out of sulfates, which means water was involved, but slightly different climate going on. And then a lot of Mount Sharp at the very upper levels is just completely dry and probably never saw water. And so there was a lot of environmental changes that are recorded in Mount Sharp. So as we were driving across the plains in that 15 months to Mount Sharp, we started seeing a bunch of rocks all in kind of the same pattern. And when you're looking at this picture, imagine you're driving along the path that we looked at earlier, and Mount Sharp is to the left of you, and the crater rim is to the right of you. And so we started seeing all these different rocks that were tilted towards Mount Sharp. And you can kind of see that in this picture. We have these beds of sandstone, sand-sized grains that are cemented together in a sandstone. And then all the little beds of rock, all the little layers are tilted towards the mountain. And that indicates, when we started looking more and more detail, knowing that we also saw those river deposits earlier with the conglomerate rock we talked about, what this looked like to us was when those rivers empty out into standing bodies of water, they can form these delta deposits. And these delta deposits would look just like these rocks in front of us. They would look like a bunch of tilted beds, and you can kind of see that in the cartoon. The river deposits would be the gravels and the conglomerates. The delta deposits would be tilted rock all facing towards a lake. And in this case, we saw them all facing towards Mount Sharp. So it's as we were getting towards this mountain, we saw more and more evidence that we were crossing ancient lake shores, which kind of was a mystery to us because there's a big mountain there. You wouldn't expect to be following a river downhill when you're actually slowly climbing towards the edge of the mountain. And what we had this realization is that the mountain wasn't there originally, which makes sense because we think it did build up over time. So sometime in the ancient past, there was no mountain, and instead there was a series of lakes. There was one big lake filling the crater that caused a certain shoreline to happen, and then mud built up in that lake and raised the lake level, and then that made the shoreline push out somewhere else, and that just went on until the mountain built up. So that's at least our theory now of how the mountain formed. And it's based on this evidence of seeing these lake deposits and delta deposits as we were getting closer and closer to the mountain. And it made a prediction. Of course, theories are really great in science when they not only do they explain a current set of data, but the best kind of hypothesis, the best kind of theory would actually make a prediction so you can test it more in the future. And so we had this idea, this hypothesis that we were looking at streams that delivered sediment to the middle of the crater, and then that sediment slowly built up the mountain. But the prediction it made is that when we got to the mountain, we should see the lake itself. So we'd seen the river deposits, and we'd seen the gravels and the deltas, but where are all the lakes? And so when we got to Mount Sharp itself, and this site called Pahrump Hills, we found the lake deposits. So it was a great way to give some more believability to our theories. And what's shown on the right is all those stacked layers of rock. And what's interesting about these stacked layers now is that they're no longer tilted towards the mountain anymore. They're flat, and they're no longer sandstones. Sandstones are coarser grains like sand that would be carried by a moving stream like a river or a stream. These are flat layers of very fine-grained rock, again like mud at the bottom of an ancient lake, and flat as if they were deposited in a standing body of water like a lake. And so we found exactly what the theory predicted, and we've spent, ever since September, we've been doing what's shown on this yellow line, where we hit our first set of lake deposits, and we went up and down this yellow path now 2 times to explore all these different sites and drill extra drill holes and figure out what the lake was like, what its chemistry was, and then how long it existed, and whether it came and went. Those are all the kind of questions we're asking now at Pahrump Hills. And that's still in work, and hopefully we'll make some more discoveries about that this coming year. So finally, along these lines, here is a little artist's rendition of what it may have looked like at the earliest parts of the history of Gale Crater, where there was water coming in maybe from snow that was up on the crater rim, and then the water filling in the crater where there now is a mountain. And the mud slowly built up in this lake, and the lake level rose, and it slowly deposited more and more of this mountain until something happened where the climate of Mars changed and the water went away, and now then something else came in like wind and kind of sculpted the mountain to the shape that we see today. What's exciting about this theory, which seems to be holding up so far, is that it really requires a Mars that's very different from today's Mars. There's just no way you could have these lakes and rivers in current Mars because it's really dry, it's really cold. There's hardly any water today, and any water there is all frozen up at the polar caps. And so it implies that 3.5 billion years ago, there was actually a much more humid climate on Mars, one that actually had a hydrologic cycle, like with lakes and oceans maybe, water evaporating and then raining out, snowing out somewhere else, and having a full cycle, hydrologic cycle like on Earth. Okay. One more science tidbit here, which is a very recent discovery that we announced in December, and this has to do with methane in the atmosphere. So we're totally switching gears here, going from the surface of Mars in the past to the present day atmosphere. It's pretty nice though. We have a really capable rover that can do all this sampling, not only of the surface but also of the air. And so we have this really sophisticated instrument, also pretty cool I think, how it works. This is called a tunable laser spectrometer. And what you're looking at, that piece of hardware in the lower panel, is about it's about a foot across, so you can hold this thing in your hands. And inside all that metal are 2 mirrors, one on each end, and a laser that shines in between those 2 mirrors. And that's what's shown on that color picture to the lower right. a laser bounces between those two mirrors 81 times, and by bouncing between those two mirrors 81 times, it's like you're shining a laser about 60 feet across Mars' surface. And that allows us to pump Martian air inside that cell, shine the laser through it, and gases in the air will absorb the laser light, just a tiny little bit, but they'll absorb it enough that we can measure the constituents of the atmosphere. And we have two of these lasers on Mars. One measures carbon dioxide and water in the atmosphere, and the other measures methane. And we were really interested to measure methane because methane on Earth, the number one way we produce methane on Earth is actually from biology, from cows and from rice fields, things like that. And so the fact that it might exist on Mars, and people have claimed to detect it with telescopes on Earth and with spacecraft at Mars, was really exciting. But we wanted to be able to measure it from the surface of Mars itself, and so we sent this very sophisticated instrument to study it. And what we found is shown on the next page here, which is that, okay, so this plot shows on the bottom from Sol 0 to 750, and Sol is just what we call a day on Mars. So this shows the entire mission, from the day we landed at Sol 0 all the way to the end of where we are now, and it shows all the different measurements with this instrument. And you can see in the early days, around Sol 100, we were measuring things that we couldn't tell were any different from 0. So even though the measurements may have been slightly above 0, the error, which is shown by the lines on above and below each point, the error was such that it was basically the same as measuring 0. So we weren't sure. But then all of a sudden, we started seeing other measurements. And I really want to point out the ones around Sol 500, where we had 4 measurements in a row that were all about 10 times higher than what we had seen earlier. And that was a real surprise. So not only were we measuring methane that was clearly different from 0, we were measuring something like 7 on these units, which are parts per billion, so a very small amount. 1 part of methane per billion parts of Mars' atmosphere. But still, we could measure it. We found a 10-fold increase. And that was really surprising because we had seen nothing before. And for methane to come into Mars' atmosphere that fast, and then disappear, because you can see afterwards we measured basically 0 again, we couldn't really explain that, and we still can't today. So what I show you next is just all the different thinking that's gone on to explain this mystery. So, you know, when you can't explain something scientifically, you kind of go to the drawing board and you think of all the different ways that you might be able to explain it. And so, you know, we sent all of our chemists back to the drawing board and asked them, you know, what makes methane and what destroys methane on Mars. We call those sources and sinks. And so if you start at the very bottom, the really exciting one is microbes. So microbes do produce methane. And then on the right-hand side, there's rocks and water. We know on Earth that rocks deep underground, when they interact with water, can also produce methane. And then you go one layer up here, and you can store that methane if you want in the subsurface. And when it's stored in kind of an ice, it's called a clathrate. Then also, now let's jump up to the surface. So let's say that, so chemicals that are flying around in space on comets and on dust particles in space, we actually know that they have organics. They have carbon and hydrogen molecules on comets and asteroids all the time. Some of those hit Mars. And once they hit Mars, sunlight, ultraviolet light from the sun, can break down those organics and also create methane. And then in terms of destruction, once it's in the atmosphere, that same ultraviolet light can destroy it, and you end up on the right-hand side of the picture, where if you have methane in the atmosphere and ultraviolet light breaks it apart, it'll form things like formaldehyde, methanol, carbon dioxide. So we want to look for all these different clues, and that's what we're doing now. We're trying to figure out, is it coming from deep underground? Is the fact that we only saw it for just 2 months in this weird pulse Does that mean that maybe it came out of the surface in what we call outgassing, like what's shown in the center of this picture? Maybe it kind of erupted from the surface somewhere. Or maybe a recent impact happened, delivered organics to Mars, and now we're seeing those organics broken down by the UV light. We're going to look for all these clues, and hopefully next year we'll see another spike in methane. If that is the case, then that'll at least give us a clue that maybe it's a seasonal thing on Mars. Maybe every spring on Mars there's a methane release. But that's been one of our most interesting discoveries recently, and one we have not yet fully understood. Okay, so I think I just said all this, so you can read all this later. I'm not going to read through these words. And I'll just end here with a little bit of questions, or a little bit of discussion about what's next. So we are now at the lower reaches of Mount Sharp. We're finally there at the mountain at Pahrump Hills, and we're going to keep climbing up later. And we drilled into Pahrump Hills. This is that same area that I showed you earlier. We had the golden path drawn on it. This is the site we've been at since September, and this is on the lower right is our drill hole. These drill holes are like if you had a dime and you put it on the surface. That's about how big the drill hole is. And we get that powder. You can see that powder that was created from the drilling. Some of that powder we deliver to our laboratories and can study what Mount Sharp is made out of. And then here's our plan for the next couple of years. So we're at the top of this picture in Pahrump Hills. The lower you go on this picture, towards the bottom of the picture, the higher you go up on Mount Sharp. So every one of these lines you see across the picture is another layer of Mount Sharp. And so we want to follow the yellow path. We're going to cross through some mountains called little mountains called the Murray Buttes. And then we want to cross this thing called the Hematite Ridge. Hematite is an iron mineral that's all over this ridge. We don't really know why there's all this iron in this ridge, but we want to go figure that out. Then we'll keep following the yellow path, and we'll climb higher and higher through the clays and through the sulfates that we talked about at the very beginning. And, here's another picture. Now we're kind of looking at Mount Sharp from where we are now with Curiosity. We're currently inside the Murray Formation, which is the lowest layer of Mount Sharp. Then we're going to cross that Hematite Ridge, hit the clays, hit the sulfates, and then we'll be about 1/4 of the way up this 3-mile high mountain. But we'll have made it through all of the scientifically interesting stuff. Most of the upper part of Mount Sharp isn't really that scientifically interesting because it didn't involve a lot of water. But in the next, 2 to 3 years, hopefully we'll make it through all of the stuff that's shown on this slide, and we'll learn a lot more about the ancient environment of Mars. And I think that's my last slide. So that was a lot of stuff. Hope you found it interesting. And let's go for some questions.
All right, folks, so the way we're going to do questions is the way we've done them previously. If you want to go ahead and prepare your questions in the chat window there, and go ahead and raise your hand. The hand icon is underneath your name on the far left side of the screen, and then what we'll do is I'm going to call you in order of which the questions were received. It looks like we already got 15 questions ready to go. So we're going to go ahead and start with Rosella, then Katya, and then Natasha. So go ahead and enter your question into the chat window, and Dr. Vasavada will get a chance to read it. And wow, there's a bunch of questions for the first question. So keep in mind too that we want to kind of condense the questions as best we can. We've got about 20 minutes here, and we've got close to looks like 16 people now. So all right, there's the first question.
Okay, that's a lot of questions. Let's see. I'll just go quickly through them. In terms of flying rovers, I think, like you say later on, we're going to work on that helicopter. But for now, it's pretty difficult to land on Mars. And of course, just like on Earth, like in airplanes, taking off and landing is really risky. So we kind of work our way up. Driving was a big challenge that we only learned how to do in the last 15 years or so. And so, hopefully one day we'll be able to have things like a helicopter or another kind of spacecraft that can land multiple times all over the surface. Let's see. where can I find more info about the helicopter? I think on JPL's website, we just had one press release, which is probably the one you saw. That's all the information that's out there right now because it's brand new and still being developed. Let's see. I'll just go for one more of these. How does the ChemCam laser work? I briefly mentioned that earlier, but it's basically a laser that shoots light at about 1 micron wavelength, and then it shoots that laser and focuses it with a telescope up to about 20 feet away, and we create little sparks, and then that same telescope images the laser sparks with a spectrometer, so we can see all the different wavelengths of light and colors that come back. And those, when we look at the light that comes back, different chemicals in the rocks have different signatures in the spectra, in what wavelengths of light are emitted back. And so that's how we can measure things with ChemCam.
All right, Katya, you're up next. Natasha, and then Michelle after that.
Okay, Katya says, what is the life expectancy of Curiosity, and what is the current status of the tires? And how will this hurt or help us or delay us in climbing Mount Sharp? Good questions. So the life expectancy of the rover, there's a few different ways I can answer that. And of course, I don't have like a perfect answer because we've never done this before, so we don't really know, statistically how long it's going to last. But one thing is we build things at JPL and, of course, at all the other NASA centers in a way that we do our best to guarantee a certain lifetime, and we do that by testing them in a certain way. So everything on Curiosity was tested in a way that we think it'll make it last at least 1 Mars year, so 2 Earth years about. So things were put in hot and cold chambers and radiation and all the other things that would cause them to fail for an equivalent time of 2 years on Earth. And that 2 years just ended for us. So the warranty kind of just went off on Curiosity, but we're not too worried because when NASA tests something to last 2 Earth years, it's probably going to last a lot longer than that. And so we're running, after our warranty now, and nothing really has broken so far, thank goodness, except for the wheels, which we'll talk about. And then the one thing we do know, though, is that we have a nuclear power source, and that nuclear power source degrades just slowly over time. And we think we'll have plenty of energy for at least another several years, 3, 4, 5 years. Then we'll have to start cutting back on what we do, and then slowly the energy will go away. Now, quickly about the wheels. We, about a year ago, were taking pictures of our wheels just to monitor them and started seeing a lot more little tears and punctures than we ever had anticipated. And, of course, we stopped driving right away, and for like about 2 months, we did a pretty detailed study of what was causing that damage. So we had all these geologists weigh in looked at everything we had driven over and saw what was causing the damage. Then we had a bunch of engineers at JPL set up test facilities to see if they could reproduce the damage by using those kind of rocks that the geologists thought might be causing it. And then also, very importantly, to then, once we figured out what was causing it, see how long we had left. So we could simulate in the test bed the damage we'd gotten so far, and then because it's the test bed and not the real rover, we can run it forward. We could say, okay, now run another 10 miles we made a circular track on the test rover, ran another 10, 20 miles, and we saw how the wheels eventually completely wore out. So now with all that information, we know how to drive more safely, how to avoid certain rocks, and we know just about how long we have left if we drive safely. And we do think it's enough to get us all the way up to this sulfate unit and what we want to do with the mission. So thanks a lot for the question. That's an important one that we've been working on pretty hard.
All right, Natasha, you're up next, followed by Michelle.
Natasha asks, is there any indication that if there are certain levels of the gas, is there a possibility that an event happened in the past or to be discovered. So like a volcanic eruption or natural disaster. And you can discover that through the remnant gas in the atmosphere. Yeah, that could totally happen. And in fact, that's one thing I was mentioning with methane, is one explanation for that little bit of methane that we discovered for a 2-month period when it spiked up was that it was a recent comet or asteroid hitting Mars that may have caused a plume and then lasted about 2 months before it was all destroyed by ultraviolet light. So we asked our friends with the orbiters to look at all their pictures and see if there's any recent impacts near us that could explain it, and they didn't find anything. So that's interesting. If a big volcano were to go off, just like on Earth, when volcanoes go off, they temporarily change the composition of the atmosphere. And so if that happened on Mars, we should be able to detect that as well. And as of right now, we don't think there's any active volcanoes on Mars' surface. But if we did see one with the pictures from orbiters, we could probably sense it chemically with our instruments. There's other things too. We know where if something caused some of the polar caps to melt all of a sudden, really they wouldn't melt. They would sort of evaporate and cause a lot more water in the atmosphere. That's something we could probably see also. So,
all right, Michelle, you're up next.
Okay, Michelle asks, what location on Mars would be the most interesting to explore, and what makes it so interesting? Well, that's a good question. You know, we spent a lot of time thinking about that for Curiosity, so that's, of course, I'm really invested in Gale Crater and Mount Sharp because of the goals of our mission. We wanted to look back at what may have made Mars habitable 3 billion years ago. So we found this great site with this big record of geologic change captured in the rocks of the mountain. So I really love this site. But there's, of course, a lot of other things going on Mars, too. And one of my other favorite sites is the polar caps. The polar caps actually have layers of ice, many, many layers of ice. And you may be familiar with the fact that scientists on Earth go drill big cores of ice in Greenland and Antarctica. They'll just go get like 100-foot column of ice and then study it layer by layer, because on Earth all the records of recent climate change are trapped in that ice. That's how we know how the glaciers came and went 10,000 years ago, 100,000 years ago, a million years ago. And the same kind of thing might be true for Mars. That would all be very recent climate change on Mars, like the last 1 million or 2 years, whereas what we're studying in Mount Sharp is about 3 billion years old. And there's a lot of other really cool sites on Mars too, where we think there might be evidence of a little tiny bit of liquid water today in sites that are called gullies, but there's so many places and so few rivers. Next one.
Okay, next question. I'm not really sure how to pronounce that first name, so go ahead.
Okay, this is, I gotta read this one, it's long. Okay, the atmosphere is thin, and therefore not enough pressure for water to be liquid, which is true. Planet's cold, so it makes it harder to be liquid, that's also true. One way to fix this is having more greenhouse gases, such as CO2. And a good source of CO2 is volcanoes. And so what if you had, basically what if you had current volcanoes? And could that put in a bunch more greenhouse gases and change Mars into a planet that could support liquid water? That's actually what we think happened in the past. So one of the explanations for why Mars may have been a lot more wet in the past, in the first billion years or so, is that the atmosphere was thicker. And it solves the problems that you've listed, which is that a thicker atmosphere would both have enough pressure for water to be liquid. Right now, water on Mars would turn directly from ice into gas, and it's hard for it to be liquid because the atmosphere is so thin. But a thicker atmosphere would solve that. But then even in the thicker atmosphere, it might still all be frozen. So you also have to have a warmer atmosphere. And the fact that CO2 is a greenhouse gas, carbon dioxide is a greenhouse gas, if you had a much thicker carbon dioxide atmosphere, you could get some of the way there. But currently our models show you won't get warm enough. So we have to have additional greenhouse gases, like sulfur dioxide or like hydrogen or even methane. And we still have a hard time showing how we can get a planet that could have lakes like the kind I showed, but that's the current area of research, is we're trying to do that. Now, could we do that if a big volcano went off now? Could it turn Mars back into that kind of world? It would have to be an enormous eruption, or maybe like a whole series of giant comets hitting Mars could do that too. So it's possible, but we think that was a lot more common early in Mars history, because right now Mars is kind of freezing. You know, it's not only on the surface, but the planet itself. Volcanism is a lot less common than it was in the early days when the planet was warmer inside. So,
Jimmy, you're up next.
Thank you, KK. Jimmy, is that right? Okay. 2 half questions. Does Curiosity experience any loss of charging capacity due to being in the shadow of Mount Sharp? And how flexible is Curiosity's itinerary? What would change the mission plan, and how would that change be discussed and improved? Great questions, ones I deal with a lot day to day. So if you remember that picture, actually I can get back there. So back when we landed, Mount Sharp was pretty low on the horizon. So we were really not shadowed much at all, as you can see on this picture here. You know, now we're up a lot closer to it, but it's still you know, pretty low on the horizon. So it's only really it kind of looks like this now. So only, you know, right near sunset and sunrise. Well, it's actually also to the south of us, which helps a lot. So sunrise and sunset are kind of east and west, like on Earth. So it's really not too much of a problem to get shadowed by it. I think the bigger problem is going to be something like this, like when we actually start driving into some of the little canyons you can see on this, where the walls of the canyon will be really steep on either side of us. That's when we'll have problems not only with shadowing, but also with communication to Earth. So we need to have a good signal from our antenna on the rover to be able to see Earth in the sky. And that's going to be a problem that we'll have to figure out. We'll have to maybe drive only on some parts of the canyon walls to make sure that we always can see the Earth. Yeah, your other half question was the itinerary. So we have to have like a strategic plan, like what's shown here. We know we want to explore Mount Sharp, and we know we want to get all the way to the sulfate layer in the lifetime of the rover, which is maybe another 3, 4, 5 years when we're very active, before the energy starts running out. And so, you know, it's my job to make sure that we're still progressing towards that endpoint. But there is flexibility day to day, of course, in what we do. We can drive left, we can drive right, we can go check out something we just saw in the picture yesterday. And there's even flexibility on the month-long time scale. You know, we decided to spend a year at Yellowknife Bay, and we didn't know that at all before the day we landed. But because the science was so important to discover this habitable environment, it was worth it in the end. And same with Pahrump Hills. You know, it's the site we've spent 5 months at now. But because it's the very first rocks that we're tasting Mount Sharp, we wanted to really get to know the place. And I think now, after we leave Pahrump Hills, we're going to be driving a lot more because we want to get on with things and make sure we get up to these sulfates. And how does it get approved? It gets approved mostly through our 500-person science team, where, you know, I'm the lead scientist on the mission now, but I have another 20 or so key scientists that all weigh in on the big decisions, and then we make decisions.
All right, David's up next, followed by Grant and then Victoria.
David. Okay. What do you feel is the most crucial information about Mars that we need for future manned missions? And how do you propose that we can go about getting that information? You know, NASA's working pretty hard on answering that question. I can think of 3 off the top of my head. One is to understand the environment that astronauts will have to deal with. So we're measuring radiation, which is a big one because radiation would be very harmful to you. The cancer rates, et cetera, would be extremely high if you were to just go to Mars in a moon-like spacesuit. So we have to have new technology for where we live on Mars to make sure we're safe from the radiation. We also have to know the temperatures and even things like how much dust there is, because dust will just get over everything on Mars. I mean, it'll just get over everything. So we have to invent new ways of keeping dust out of all the systems that astronauts use and know how cold and hot it is. And then we're learning how to land bigger things. So with Curiosity, we landed something that was 5 times as heavy as the rover before it. And then for a manned mission, we probably have to land something that's 10 or 20 times even heavier than Curiosity, if not more. So we still have learning to do there. And we learn that just by trying it, by sending things, designing things, and seeing how they work. There's a whole lot of other things you have to know, but we're making progress with all these missions.
All right, folks, we got about 5 minutes left, so we might not be able to answer all the questions, but we'll try to go a little bit quicker. You might have to scale down your questions. Well, maybe only answer one of them. But Grant, you're up. Victoria, then Nathan.
Okay, Grant, are you recording the isotopes in the rocks you study? If so, can you build a record from some sort of isotope dating? Thank you. Okay. Thank you for asking. If you didn't know about what we've done so far, then you're a great, straight man for my talk here. So you fed me a great line. We have age-dated rocks on Mars, which is super exciting. We didn't even know we could do that before landing, but we found a way to use our laboratory to look at the isotopes of certain certain elements in Mars surface, argon, nitrogen, and helium, all of which are caused by cosmic rays hitting the ground. So cosmic rays hit the soil. They create these rogue isotopes of argon, helium, and the other one I said. And using those, we can figure out how much of those elements built up through cosmic rays. And the longer something has been sitting out on the surface of Mars, the more cosmic rays have hit it. And so the amount of those elements tells us how long it's been sitting there. So that's called cosmogenic age dating. And we did that at Yellowknife Bay, and we got an age of 80 million years. And so that told us that the rocks of Yellowknife Bay had been open to space for 80 million years. And before that, they were buried. We also did the other kind of age dating that you mentioned about just how old the rock is. And that came out to about 4 billion years, which is what we kind of thought. So that one wasn't too interesting, but the 80 million years one was really interesting because that tells us how long it's been since erosion cleared out the area and exposed Yellowknife Bay to the Mars environment.
All right, Victoria, you're up next, followed by Nathan.
Victoria says, could Mars have had a spinning liquid core? This would intensify the magnetic field and shear the atmosphere and solar wind, prevent the loss of greenhouse gases. Yeah, these are like really smart questions, so thank you for those. That's exactly what we think happened early on. So when I told you the story about how Mars had a thicker atmosphere in the past, and that allowed liquid water to form and survive in lakes and oceans, what allowed that atmosphere to survive then, and then what then caused it to be lost to today, was actually the presence of a magnetic field. So like on Earth, which has a magnetic field and it's shielded by loss from the solar wind, in early Mars history, Mars had a liquid core, and there was circulation within the core that or mantle that allowed a magnetic field to be present. Once that magnetic field was lost, maybe 500 million years after Mars was formed, something like that, then Mars became vulnerable to the solar wind hitting the atmosphere and eroding the atmosphere slowly over time and causing it to shrink to where it is today.
All right, we got time for 1 or 2 questions, so let's go with Nathan and Jackie.
Nathan says, how does the MMRTG radiation influence the RAD readings, our radiation detector? It does, but in a very specific energy level of radiation, so we can just ignore that one reading and look at the rest of the radiation. So that's your quick answer. What are the materials made out of? Aluminum, flight grade, aircraft aluminum kind of thing. It's an engineering project, so a successful engineer neither has too much of something or too little of something. You have to get it just right, and that's what's been a challenge. So we thought we understood Mars enough to pick the thickness of the wheels we used, but it turns out we were just a little short on that. But in the next rover, we'll have a little thicker wheels for us to prevent the damage that we saw. And the treads, we don't have any kind of treads on this rover. We just have the 6 wheels that have individual treads, but no Caterpillar tracks.
All right, Jackie, you're up next.
What happened to the water in Gale Crater, and does it still exist beneath the surface as ice? Good question. So we think the most likely explanation is that the water evaporated. So when, at some point the Mars atmosphere was thick and humid, and then the lakes could survive there and be replenished by rainfall and snowfall. And then when that changed and the atmosphere started drying out, the first thing that would happen is probably the lake would just evaporate into the air. If Mars got cold at the same time and some water was frozen in the ground, eventually that would probably be lost too, because eventually the dryness of the atmosphere would penetrate into the soil, and even ice would sublime away. So we don't think something like the equator, where it's warm and dry, would have any ice at depth. But we do think there's ice at depth, closer to the poles.
All right, Christian, I think you're going to have the last question. Go ahead.
How important would it be to get samples from the subsurface about 3 to 5 meters? Would it be useful? And how deep would we find ice water? Okay, so second part first. I'll just answer at Gale Crater, we don't think there's any water even hundreds of meters deep. Up near the poles, the closer you get, the more shallow the permafrost layer is, and right near the poles there's ice just a few centimeters below the surface. If you look up the Phoenix lander from 2007, it actually dug a trench and found ice. So then your first part here is, how important would it be to get samples from 3 to 5 meters depth? It is important because of the radiation we talked about. The cosmic ray radiation penetrates a few meters into the surface, and that cosmic ray radiation destroys any evidence you would have of ancient life or organics. So radiation, just like when you get a sunburn from ultraviolet light on Earth, in a similar way, ultraviolet light and cosmic rays will go into the soil and break apart organics so that we can no longer study them today. So, just tying it back to the cosmic, to the age dating question, one of the things that we were excited about by getting that 80 million year old age for the rocks at Yellowknife Bay was that in 80 million years, there's still a chance that it hasn't been exposed long enough at the surface for the cosmic radiation to damage it. So you have sort of 2 choices. If you want to be really safe, you drill 3 to 5 meters, like you said, to get below the surface that's been degraded by radiation. But if you want to be kind of novel and use Curiosity's results, you can look for places where the geology tells you that there's been erosion. And if that erosion has happened in less than, faster than just a few tens of millions of years, like we think it did at Yellowknife Bay, if it's very recent erosion, then you sort of have a natural bulldozer. It's working over millions of years, but that natural erosion is sort of plowing away the upper few meters of surface and giving you something that hasn't yet been damaged by radiation. So you can use geology as a natural way of getting down to a few meters depth, or you can figure out how to bring a big drill to Mars. Or explosives. I always like that idea, where you bring a little hand grenade with you, but I don't think NASA will ever do that. So with that, thank you very much. It's been fun. Thanks for all the great questions.
We appreciate the presentation, Dr. Vasavada. That was fantastic. I know we all learned a lot. A couple quick announcements before we wrap everything up. Students, just remember that your final projects are due 2 weeks from today. That's Monday, February 9th. We ask that you continue to send information to your instructional assistants to make sure that you get your final project completed on time. If you're at the same school or institution with someone else, encourage them to obviously get through all 3 modules and submit their final project. At any point in time, if you have problems with getting in touch with your instructional assistant, or you have some questions that just need to be answered quickly, you can always email us at the NCAS email box, which the information is on Moodle. You can find the email address there. You can always contact us there. I check that on a daily basis as well. So we hope that you guys will continue on with your work. We're looking forward to obviously getting our selections made for the on-site experiences. So we hope that you guys are excited about that as well. We appreciate your time this afternoon, and with that, we're going to go ahead and wrap things up. Actually, there is a let me field this question in the chat box. The email was bouncing back from Katya. So if you're having problems sending it to the NCAS email box, you can go to the Aerospace Scholars website, and there's contact information there. You can contact us there as well, so try that as a secondary option. But traditionally, yes, that is a correct email address. So try not to send it through Moodle. Maybe you can just send it directly, and we should receive that. But with that, we're going to go ahead and wrap things